Yeah, well, thanks very much, Ezra. The material on which this talk is based is joint work with Karthik Bharat and also Huiling Lei, both colleagues from Nottingham. I think probably some of you know them. So I'm going to start with we'll start with a fairly brief review of it. Empirical likelihood EL for Euclidean data. Yeah, I'm then going to say a few words about EL for manifold-valued data, and then move on to open books. So the open book is a type of stratified space, and then I'm going to talk about work which is sort of about 3 or 4 days old, and and looking at a further example of a stratified space. Right, okay. Please feel free to ask questions during the talk. Oh, and I forgot to say a thank you to the organizers for inviting me to what's proving to be a very interesting meeting. Right, so some of you will know about empirical likelihood, some of you may not. So it's a type of non-parametric likelihood, and it's supported on the sample points. So one uses a model which is based on, that's where the probabilities are associated with the sample points, and it leads to some interesting properties that will be discussed later. Yeah, and what I want to do in this talk is, first of all, to show that EL is useful in non-Euclidean settings. I mean, it's not sort of going to solve all one's problems, but I think it's certainly a useful part of the toolkit. At least that's the way I look at it. And so I want to try to bring that out. And the second thing I want to talk about empirical likelihood in stratified spaces. Now, what sort of things is empirical likelihood useful for? Well, it can be useful for basic things like, for example, constructing a confidence region, or for example, if you've got several populations and you've drawn samples from each of those populations, and you might want to test whether some characteristic or some parameter is constant across those populations. So in this type of problem, we've got two populations, F1 and F2, and so we have a parameter, and we're interested in some informal statistical language. We want to test the null hypothesis that θ1 equals θ2, and the alternative is that θ1 is not equal to θ2. And more generally, we could have K populations. So there are two versions of this problem. So with one of them, so one version boils down to testing whether the two populations are actually equal. So in the sense of sort of having this, in the sense of being described by the same distribution. Yep, sure. Yep. Yeah, and but version 2, I think, is usually the more relevant type of the more relevant two-sample problem where nuisance parameters are present. So, for example, we might be interested in Fréchet means, say testing equality of Fréchet means, but without assuming that the dispersion structure is the same in the two populations. And empirical likelihood, I mean, you can do either, but it's more noteworthy that one can conveniently do version 2. empirical likelihood for Euclidean data. So we define a probability distribution on the sample points, and I'm going to assume that continuous data, so that ties don't, so that with probability 1 ties don't occur. And for example, if we look at the say the sample mean, so if that's the parameter that we're interested in. Did I? I should have just said that that there's that parameters can be thought of as functionals and functionals can be thought of as parameters, where the functional is on the space of distributions. So it's just something to bear in mind. And here the function is the mean functional. So what does empirical likelihood look like for the mean function in Euclidean space? Well, it's really just so the empirical likelihood at a point mu, which lies in R to the P. So we're assuming that the xi's are that they're in R to the P, and so to calculate the empirical likelihood at mu, we solve this optimization problem, and it's a nice optimization problem. The objective function is concave, so it's a minus. The objective function will be convex, so it's it's a convex optimization problem with a linear constraint, and there isn't a closed form solution. But the solution is unique when it exists, and to find the solution, you just need to solve equation 3 for lambda. So, and there are very fast, and reliable algorithms for doing that. So, and that's what leads to the probabilities on the sample points. So for example, pi mu, so that's the probability associated with observation I, when we're calculating the empirical likelihood at mu. And one useful fact is that it turns out that minus log of the empirical likelihood at mu is actually a convex function of mu. And that turns out to be quite useful in various contexts. So it's not immediately clear why empirical likelihood works. So I'd just like to say one or two things about that. So let's first.
The definition of EL went by really fast. Can you just put the slide up again for definition?
So you mean equation 2? So we're maximizing the product of the PIs. So the PIs are the probabilities that sum to 1. And subject to P lying in that space. So in other words, the PI sum to 1. That's curly P, and then we've also got the linear.
This convex combination being mu.
Yes, exactly. Right. And then we optimize that over the P's.
Got it. Okay, thanks.
Well, thank you for asking anyway. So it's actually slightly more convenient to look at the log empirical likelihood ratio, or twice the log empirical likelihood ratio. And that just turns out the only thing that really changes is that you put the n in here. So the point here is that under the alternative, the optimal is to take PR equals 1 over n. And that's because that's a sort of global optimum for the empirical likelihood when the p's are unrestricted apart from satisfying the equations in 1. Okay. So that's the empirical the log empirical likelihood ratio. And this is so that's a form of Wilks statistic, and it now for parametric models. So in standard parametric models, Wilks statistic satisfies the following: that when the null hypothesis is true, so in this case, it's mu equals mu zero, where mu zero is pre-specified. The Wilks statistic converges in distribution to chi-squared with p degrees of freedom, where p is the dimension of mu. So under very mild conditions, that holds. I mean, when the covariance matrix has less than full rank, then the p should be changed to the rank of the covariance matrix. Yeah, and so this result is sort of classical for parametric models, but it also holds for empirical likelihood. Yeah, and why? Yeah, and why is that? Well, I can give some insight into that by looking at what happens for large n, and it turns out that under the null hypothesis, that the Wilks statistic, that the leading term in the expansion of the Wilks statistic for large n, it turns out to be that expression there, which is so v hat is the sample covariance matrix, yeah, and mu hat is the sample mean, yeah, and this and this converges to a chi-squared, and we also have the negligible remainder term in 5. So that's the key insight into why it works. Okay, how am I doing for time? I should probably move on a bit. So yeah, I think I'm going to skip some of this other stuff on higher order properties because that's not really essential to the talk. So yeah, if anyone's interested in asking about some of the higher order properties, we can talk about that later, but let's leave that for now. So let's now think about empirical likelihood for manifold data. So in section 2, we looked at an empirical likelihood for Euclidean data, and in particular for a Euclidean mean. There have been one or two earlier examples of using empirical likelihood. But very recently, there's been a paper by Kirisu and Otsu. I think it's actually 2024, so from last year, and well, and they developed an interesting approach to empirical likelihood. But one thing but they do things more generally, and they look at generalized Fréchet means rather than Fréchet means. And I think it's fair to say that the story is quite a lot more complicated for generalized Fréchet means. So
generalized means the Fréchet means set?
No,
Go ahead.
no. It means that you're somehow matching the object, the space where you observe the data. You're matching the observation with something in some other space.
It would be geodesics, for example.
Yeah.
You're finding best geodesics for P and S subspaces.
Yeah. So it's potentially much more general than I'm thinking about here. But I'm still going to say something about the standard Fréchet mean case, because I think there's a simplicity in focusing on sort of standard Fréchet means, which that's maybe lost when one looks at it in terms of well, at that level of generality. Or although I do think that it certainly it has many useful applications of what they've done. So yeah, so let's now look at so first of all, I should define the Fréchet function. We've seen it defined several times earlier during earlier talks. So we have the Fréchet function G subscript f. So f is the distribution. Yeah, and I'm going to assume in this talk that the Fréchet mean is unique. um, yeah, and the sample Fréchet mean is defined replacing the expectation by the sum divided by n. Yeah, I think it's just worth mentioning that there are two versions of uniqueness. There's the strong version, which is that there's only one local minimum, and there's the weak version, which is that there may be more than one local minimum, but there's only one global minimum. Yeah, I'm going to assume B here. Yeah, probably A is probably too strong for many statistical applications, but not for certain types of spaces, but for example, spaces of positive curvature. So, yeah, let's just look now very briefly at how one can set things up for manifold data. So using this result here, which I think is a fairly standard one, that the gradient of the squared distance in a Riemann manifold is minus twice the log map, so that's x minus 1. That's the log map. Yeah, and so interchanging the order of differentiation and integration, the Fréchet mean will satisfy that the gradient is 0. So
X naught is the Fréchet mean.
yes, yeah. So x naught is the Fréchet mean, so that's defined there. Yeah, and we end up with 0. So this immediately suggests how one can use empirical likelihood. So replace the integral by the sum of the PIs. No. But why is that? Oh, yes, if the cut locus carries no mass. Yeah.
It does.
Yeah. So, yeah. So we can, so this suggests that we can define empirical likelihood on the manifold. So I've changed the mu to an x. So the x is a candidate Fréchet mean, but sample Fréchet mean. Yeah, and then it turns out that we solve exactly the same optimization problem. The only thing that's different is that we use the x at which we calculate the empirical likelihood. Yeah, so that's the base for the log map. Yeah, and and the other thing that changes is that we want to for the left-hand side sum to be 0. So as long as one can calculate the log map somehow, we have a way to do empirical likelihood, and you can do the things that we mentioned, for example, to construct a confidence region or to do a two-sample test or something like that. Now there is sort of an interesting thing going on here, is that there are situations where the central limit theorem for the sample Fréchet mean can have complications. Yeah, and an interesting thing is that that using empirical likelihood somehow sidesteps these complications. First of all, let me just say one or two words about what complications can arise, and they've been mentioned in they were mentioned in Stefan's talk yesterday. So one type of issue is related to the cut locus. So So for a point on a sphere, for example, if we think of the sphere as embedded in Euclidean space, then well, the cut locus of and the x is a unit vectors, then the cut locus of a point x on the sphere is minus x, and and generally, manifolds with positive curvature, they have non-empty cut locuses. And there's a the paper by Thomas Hotz and Stefan, who look closely at what can go wrong and what can go wrong in the circle. And I'll just briefly quote this result. So they derived a central limit theorem for the Fréchet mean theta hat. This is on a circle using, so that's using the angular distance on the circle. And it turns out that the covariance has this form here. And you can see that the F0 is the population probability density evaluated at, maybe I've got this the wrong way around. I think it should be pi. Yeah, I think so I've slightly mangled the notation, but that should be pi, which is the, so that's the antipodal point to the population Fréchet mean. Yeah, and when that density is larger than 1 over 2 pi, so I think there are a few typos on this sheet, then the denominator is negative and things blow up. And they also look at what happens in the limit as the F0 or the F pi approaches 1 over 2 pi and so on. But so the point here is that there are serious problems for the Fréchet mean in this situation. But recently there was a result which proves a central limit theorem which that allows the cut locus to well, a neighbor of the cut locus to have positive density, but where a central limit theorem can be derived. I'll just write down sort of the form of the central limit theorem under fairly mild regularity conditions, and also the condition that the cut locus has 0 mass. So I'm assuming that as well. So the phi here is like a Hessian, and the H0 is the standard Hessian, but the J0 is a term or a matrix which comes from the bad behavior at the cut locus. So it's a bit like what happens with the ordinary sample median. So you may remember that the asymptotic variance of the sample median is some constant divided by the density evaluated at the sample median. And roughly speaking, something that's related to that is going on here. So I think of it as more being a matter of the irregularity, the irregularity in the estimating equation, rather than something specifically to do with the geometry. But there are also other problems which can arise purely from the geometry, as has been shown by Benjamin Eltzner. So,
what is J0?
Well, this is a term which I'm not writing down. It's too complicated, but it's but that's the term which comes from the bad behavior at the cut locus. Yeah, and
Is codimension 1 cut locus?
yes, yeah. Well, I haven't. Yeah. So the so when the codimension is 2 or more, then J0 is the zero matrix. But when the codimension is 1, then you get a matrix which it's non-negative definite, So, so when you choose the density to make that large enough, then eventually the Hessian will not be positive definite. So things break down. So there is a close connection with cut locus Wilksmirianus. Yeah. So anyway, so these things can arise when they do typically arise when you've got codimension 1. So in other words, when the cut locus has dimension just one less than the dimension of the manifold, and so what this tells us is that. So the interesting thing is that the empirical likelihood sidesteps the complications that arise from the central limit theory for Fréchet means. The problems that can arise, and nevertheless we get sort of standard asymptotic behaviour, or seemingly standard. So it's an interesting. So it's an interesting consequence of using empirical likelihood. Now the obvious point that we need a log map, and there'll be many manifolds for which the log map may not be so easy to work with, but I think one can derive it numerically. But with my statistical hat on, I would say that for manifolds with positive curvature, that life is much easier if you work extrinsically, and that's what I would certainly do myself in practice. The advantage of working extrinsically is not so much to do with the theory, but just computationally, it's so much easier. At least for the manifolds of positive curvature that one that typically arise in statistics.
That you need to have and trust your embedding.
Yes. So I think, but yeah, I'm not really talking about very general manifolds, but things like the Grassmann and the Stiefel manifolds, and I think for those things, I think they were fairly natural embeddings. But certainly when you move beyond that, then it's a different story. Yeah.
Is the EL method accurate in this situation?
Yes, I think if you use bootstrap calibration, which I've skipped over, then it's very accurate. I mean, it tends to work very well. But provided the sample size is not very low. But for example, a sample size of 20 for points on the sphere would be more than enough for. Well, I should also say that one's assuming that the maybe that the distribution is not too close to uniform if it's at least got some concentration around the Fréchet mean.
So I'm a little confused. So basically, do you think the sample Fréchet mean is an obsolete method?
No.
Or
no.
Because you sidestep the complication.
Sorry. I'm really thinking about inference for the Fréchet mean. So I'm not. But the thing about using empirical likelihood is that you can do inference for the Fréchet mean, but you're not really working directly with the the sample Fréchet mean. So it's a bit. So it really comes back to the way that we've defined the empirical likelihood. I mean, we just choose a point X in the manifold M, and then we calculate the empirical likelihood at that point. But in doing that, we don't need to actually calculate the sample Fréchet mean. And we're able to do inference without actually having to work with the sample Fréchet mean.
As we were in this discussion, I wonder whether this has something to do with Hans CLT for the variance. which also does not suffer from any smeariness. So
Yeah.
I guess it feels like there's a connection.
Yes, yep. Yeah, maybe I should try and finish the talk because I haven't even come on yeah.
Just a quick notational
Yeah.
question, is the
Yeah.
WX naught, is that a quadratic form?
No, it's it's twice the log of the empirical likelihood ratio. Yeah. Yeah. So, yeah. So anyway, so yeah. So yeah, I think there are maybe some more things to talk about later. Okay, so let's now move on to open books. So, but first of all, let's give something like a general definition. I'm not sure if this will satisfy Ezra, but I would say that we think of a stratified space as being having spaces of different dimensions somehow stuck together. Yeah, and these so these components are known as strata. Yeah, and the open book. Well, I can do my 30-second practical class. So if we think of there being a finite number of pages, yeah, and then we have the spine, so we can think of that as being one-dimensional, and we can think of each page as being as being a half space. Yeah, and then yeah, and the only way you can get yeah, we use Euclidean distance within when looking at the distance between 2 points on the same page, but when moving to a different page, one would think, say you got 2 points here, then one would think of moving sort of in a straight line, but after doing this folding. So. Yeah. Okay. Good. Good. Well, I can move on then. Yeah. Yeah. And there are some interesting examples of stratified spaces. So trees and graphs and persistence diagrams from TDA, which I think Ezra will be talking about, and yeah, and various other things. Now, mathematically, we can write the open book. So just think of the so there's a one-dimensional stratum, which is the spine of the book, and we also have the half spaces corresponding to the pages, and they're all stuck together. Yeah, and so we can think of the space as consisting of the spine. So the S is the spine, and and the L1 through to LL. So the O means interior, and we're just saying it's the union of the spine and the interior of the pages. Yeah, I think how am I doing for time? Yeah, so we can, yeah, and there's something important called the, so the distance I mentioned, so for X and Y on the same page, the distance is just the standard Euclidean norm. But when on different pages, one does a reflection, so which really corresponds to just moving the other. So if X is on that page and Y is on that page, then you would move them so that they form a whole. So that they form an R2. Yeah, and then and that's what the R is doing here. Yeah, and this is called the folding map, which plays an important role. And but yeah, that reminds me, I think I haven't mentioned the, did I mention the, sorry. There's a very nice paper by Hotz et al., which that derived the central limit for the open book. So, and the notation used here is similar to what's used there. Yeah, and to cut a long story short, there are three cases that that can arise when one does inference for the Fréchet mean on an open book. One thing I should mention is that the population Fréchet mean is unique for an open book because it's the type of space which they're called Hadamard spaces, and they have negative curvature. Yeah, and the Fréchet mean is unique in the strong sense, so there are no local minima to worry about. Yeah, and three things. Yeah, and when the population Fréchet mean lies on the spine, then that's known as the sticky case. And the condition for that to happen, well, that can be expressed in terms of the folding map. Yeah, and so if we think of the X as being so the X is a randomly chosen point on the open book, such that but from the distribution that we're considering to be the population distribution. Yeah, and when for each page, the expectation of the folding map, is negative. Yeah, that corresponds to the sticky case. Yeah, and that's where well, I'll say what happens in this case in a second. Then the second kind of situation to consider is the non-sticky case, and that's where one of the folding maps, the expectation of one of the folding maps, the first component is positive. And that corresponds to the non-sticky case. Yeah, and then the third case is sort of intermediate. That's called the semi-sticky case, where one of the for one of the pages, the expectation of the folding map is precisely 0 in the first component. So I'm afraid you'll just have to take this on trust, but these are the three situations that can arise. Hang on, have I? Yeah. So so we're working in general dimensions. So the spine has dimension p minus 1, and the pages have dimension p. So in the first case, the limiting distribution, that's chi-squared p minus 1. So it's as though asymptotically we forget about the structure of the open book, and we just focus on what happens on the spine. In the second case, well, the population Fréchet mean is on a page, and asymptotically we forget about the rest of the structure of the open book as n goes to infinity, and we end up with a we end up with a chi-squared with p degrees of freedom. But then the most interesting case is the semi-sticky case. Well, and here we end up with a mixture. So with probability half, it's chi-squared with p minus 1, and with probability half, it's chi-squared with degrees of freedom p. And these are independent sort of chi-squared distributions. So that's basically the story here. So it's really in sort of case 3 where we see the effect of the open book geometry. Right. Okay. So, yeah, I've just got to, so I'm now going to say a few words about the for the open book, the difference in dimension between the spine and the pages is, well, that's one. But an interesting question is what happens when adjacent strata, when the code dimension is more than one. So an example that Wheeling says, Wheeling suggested to me a few days ago, with the example here, and it turns out to be very simple. First of all, I haven't defined the e's correctly. The e's should be sets of this form where the x's and y's are positive. So I haven't quite written the e's correctly. And we have so the space is the unit of the origin or the union of the origin. Well, and these e's, and that's sort of a bit like pages, but not really, because we're working in a much higher dimension, a much higher dimensional space.
So it's a spider with two-dimensional legs?
It's sort of.
Just a bunch of two-dimensional planes using the first two coordinates, the third and fourth coordinates.
Yeah, exactly.
The sixth coordinates. You take those two-dimensional planes and you glue them all at the origin.
Well, that's exactly right. Yeah. And then, but then the relevant distance function. So for u and v on, so for u and v in the same E space, we just use the Euclidean norm. But the only way you can get to other two-dimensional spider legs, thanks for that, Steve, is to pass through the origin. So that's why we just have the norm of u and the norm of v. Now the analog of the folding maps here. So this is a bit different, but when they're on, so the folding map, well, it maps these E spaces, which they're subspaces of R to the 2k. So we map it on to R squared, and when the alpha here and the beta here are the same, then we just take X alpha and Y alpha. But when they're different, and we also have the Xi, which is sort of a candidate Fréchet mean, but in the R2 space. I mean that's that sounds a bit garbled, but but that's the folding map we need. So but there's also another map that we need, and this is actually the relevant one for what I want to say in the next two slides, is that we also need a map for delta alpha. So if u lies in E alpha, then we take the norm of the vector X alpha Y alpha, but we take minus the norm when u's not in the space E alpha, and and there are three cases. So it's not so different from the open book once you get to this point. So when all of the expectations of the delta alphas evaluated at a random u, when they're all negative, that corresponds to the sticky case. When one of them and only one is positive, because at most one can be positive. And when one of them is positive, then we're in the non-sticky case. Yeah, and in so in the first one, we end up with a chi-squared with zero degrees of freedom, which is just a fancy way of saying that the sample Fréchet mean converges to the origin. Yeah, and in the second case, we get chi-squared with 2 degrees of freedom. Yeah, and in the third case, we end up with this mixture here. So it closely parallels what happens for the open book, but the only difference is that we have the difference in degrees of freedom is 2, and that corresponds to the strata having codimension 2. Yeah, so one of the strata here, it's a point rather than so it has 0 dimension.
Maybe I'll ask you, maybe this is naive, but is it essentially the folding map something like this?
Yeah.
So we could think of this in R3.
Something like that.
So one guy remains that it is, and everything else gets mapped to a plane that's orthogonal to that.
Maybe. Yeah, yeah, I'm not sure about that, but
It should map the multiple.
let me just finish what I'm saying, and then we can. Yeah. So, and then finally, with some easy generalizations of the model, I think we can move to a situation where the sticky case, the limit distribution is chi-squared r, yeah, and with the non-sticky case, it's chi-squared s. Yeah, where s is a positive integer greater than r. Yeah, and in the semi-sticky case, we get the mixture of these two here. So some final comments, and then we can move on. Now I do suspect, although I'm not sure, and I haven't really thought carefully about it, and I'm not sure if I'm the best person to answer this question, but first of all, I think one could have several. Rather than just having a limit distribution with a mixture of two components, one could have it with a finite number of components. Yeah, I'm not sure whether the So and something else I'm wondering after reading, or trying to read some of the Mattingly et al. Papers is whether there are situations where we would replace the chi-squared by some other distributions, but related to Gaussians, perhaps. Yeah, and are there useful characterizations for, or maybe if not characterizations, some useful sufficient conditions for when we're in what situation. So there are plenty of open questions, but yeah, that's all I have to say now. Thanks.